Here we will show a novel efficient computational imaging method, which is light field event camera. Light field camera and event camera have already proven their effectiveness in many computer vision tasks. However, this imaging technology either suffers from high bandwidth requirement or lacking of higher dimensional attributes. In this research work, we propose a light field event imaging technology. Here is the overview of our proposed method. In our optical setup, the microlens array is placed between the main lens and the dynamic vision sensor, enabling the capture of multi-view events. For efficient processing of the light field events, we proposed the STECP method to lift multi-view events from the stream. We demonstrate the effectiveness of the system with 3 different computer vision tasks. There are 3 main changes to lift multi-view events. For noise and unsynchronized outputs, we designed EQM to manage the input events. Each microlens corresponds to a separate buffer and is marked as active when events are stored. If the number of active buffers in the neighborhood of the latest event reach a threshold, all events in the neighborhood are read out and proceed at the same time in GWMPEP, which can reduce the effect of calibration errors and pack events from the same point with the weighted triangulation. Here are some applications. First, reconstruction. We shoot the flashing digits on the monitor and successfully reconstruct the digit structure from the light field events. Denoising. Compared to the other 2 filters, we can clearly preserve the real structure and remove the background noise. Third, the tracking task. We threw 2 small balls at different distances almost simultaneously and extract the trajectory from the light field events. Both the dips and the trajectory can be extracted with the light field events. That's all. Thank you.
We present ESL, Event-Based Structured Light. ESL is a novel method for structured light depth estimation with event cameras. It excels in highly dynamic scenarios which are difficult for frame-based depth sensors. Estimating depth in these scenarios is challenging since it requires high temporal resolution and robust performance in difficult illumination conditions. ESL works by combining an event camera with a laser point projector. The projector illuminates the scene 1 point at a time in a raster scanning fashion. This change in illumination triggers an event in the event camera. For 1 scan interval, the projector traverses each of its pixels at a precise time, which allows us to define a time map over the projector plane. Similarly, for the event camera, we can define another time map which records the timestamp of the last event at the pixel location. The time maps for the projector and the event camera during 1 scan pass of 16 milliseconds are visualized here. We assess the performance of our system under various illumination conditions. Since event cameras have a very high dynamic range, they are able to perform consistently even under bright illumination conditions. In contrast, the depth errors in frame-based structured light sensors, such as the Intel RealSense, increase with ambient illumination. In the origami fan sequence, the noise in the event timestamps result in severe artifacts in the HGM baseline. While MC3D is slightly better, it also results in oversmoothing, thus losing the depth edges. In comparison, our method outperforms these approaches. We evaluate our approach on several static scenes, covering a wide range of real-world objects and environments, such as the thin structure of plant leaves and long-range indoor scenes up to 6 meters. Our approach estimates accurate depth, showing an improvement of 83% in terms of root mean square error with respect to the state-of-the-art, while requiring 60 times smaller scanning time. Lastly, we present our dataset consisting of static and dynamic scenes in challenging environments, both indoors and outdoors.
Single photon structured light. Structured light 3D imaging has inherent trade-offs balancing acquisition time, precision of scan, and robustness to high noise regimes. For instance, certain techniques achieve high depth resolution by projecting multiple patterns, but necessitate long acquisition times. In contrast, techniques projecting a single pattern can facilitate high speed, but result in loss of detail. To overcome this trade-off, we present a novel structured light technique that uses a single photon avalanche diode array or SPAD array to enable 3D scanning at high frame rates and low light levels. Our technique works by sensing binary images that indicate the presence or absence of photon arrivals during each exposure window. The SPAD array is used in conjunction with a high-speed DMD-based binary projector, with both devices operated at speeds as high as 20,000 Hz. The binary images that we acquire are heavily influenced by photon noise and are easily corrupted by ambient sources of light. To address this issue, we developed novel temporal sequences using error-correcting codes that are robust to photon noise and short-range effects such as projector defocus and resolution mismatch. Our lab prototype of single photon SL is capable of extreme 3D imaging and can operate in challenging SNR scenarios. We can scan objects with very low albedo, such as the car tire, and inverted V-groove shown here. We can also scan dynamic and non-rigid objects, such as the rapidly waved cloth and the fast-moving jack-in-the-box toy.
Hello, I'm David Lindell, and I'm presenting BACON, Band-Limited Coordinate Networks for Multiscale Scene Representation. Coordinate networks are fully connected neural networks that map input coordinates to an output signal value. For example, pixel values in an image, neural radiance fields, or 3D shapes through a signed distance function. Usually, coordinate networks can represent a signal continuously using far fewer parameters than conventional representations, such as arrays or voxel grids, which require fine discretization. However, coordinate networks are black boxes. Behavior at unsupervised input coordinates is difficult to predict, and current representations are not scale-aware, so we cannot easily ensure that low-resolution network outputs are properly anti-aliased. We propose band-limited coordinate networks, or BACON, to address these limitations. This architecture has an analytical Fourier spectrum, which allows constraining outputs of the network to desired resolution scales. We compare BACON to NeRF and MIP-NeRF on a multi-scale dataset of synthetic images. While MIP-NeRF achieves the best performance, BACON outperforms conventional NeRF models that are not scale-aware. Moreover, for low-resolution outputs, BACON uses a fraction of the parameters. Finally, we train BACON to fit a signed distance function estimated from a mesh and show the resulting multiscale representation and Fourier spectra. Fine details are preserved in the high-resolution output, while low-resolution outputs provide a simpler, smoother shape representation. Compared to neural geometric level of detail, low-resolution outputs of BACON are much smoother because their Fourier spectra are constrained. In summary, our work takes steps towards making coordinate networks interpretable and scale-aware. We believe BACON may be useful in many pipelines in vision and graphics for representing and optimizing signals while providing interpretable and transparent behavior.
Consider a camera recording two musicians practicing their acoustic guitars at the same time. While the camera has no trouble seeing each guitar separately, the camera microphone can only hear a mixture of both guitars. Even worse, the microphone is susceptible to unwanted sounds such as room echoes and ambient noises. But what if we can make our camera see the tiny vibrations of each guitar? Then we could record both guitars separately while being insensitive to the other guitar. And to the ambient noises. In this paper, we propose a novel dual-shutter imaging system for sensing low-amplitude, high-frequency vibrations. Our method can sense multiple points simultaneously and can also support object motions such as the natural motions of a guitar player. We demonstrate our method by capturing various audio sources, like a speaker membrane, a chips bag reacting to a nearby sound source,
Mary had a little lamb whose fleece was white as snow.
and various musical instruments. And there's more, like vibrational mode analysis, more experiments, and the nitty-gritty details. So come to our poster to hear all about it. Thanks.
Imagine if you are an orthopedic surgeon. You suspect that a patient has a torn meniscus, and you've got two MRI reconstructions at your disposal. At the first glance, the top reconstruction looks better. However, when you zoom in on one of the menisci, the top reconstruction contains significant artifacts. In the bottom reconstruction, you can clearly see the white streak that intrudes into the meniscus and conclude that the patient indeed has a meniscus tear. In a real-world scenario, MRI is often acquired to image a specific region of interest, or ROI. However, most existing MRI acquisition algorithms aim to recover the best full image. In this example, the top image is obtained with a general acquisition for full image reconstruction, while the bottom one is given by our region of interest adaptive acquisition. This comparison demonstrates that the optimal acquisition for full image reconstruction could be suboptimal if only some local anatomy is relevant. ROI adaptive acquisition represents a new perspective for accelerated MRI acquisition design. Instead of using a common general acquisition pattern, we propose a target-specific acquisition strategy. In this schematic example, we showed the optimized acquisition patterns for 4 knee tissues. Note that the 4 patterns are different from each other, which suggests that segmenting these different tissues call for different acquisition strategies. We want to share an interesting insight that although case-based samples encode global information, you can still optimize them for local features. Besides the motivating example for local reconstruction, our ROI adaptive acquisition also outperforms existing baselines in the segmentation task. Here we show a comparison of segmenting the patellar cartilage with an extreme acceleration ratio of 128. Thank you for watching.
In our work, we develop a novel approach for creating triangulation light curtains of arbitrary shape. To start, you might ask, what exactly is a triangulation light curtain? Well, these systems aim to selectively image a particular 3D region of space while ignoring everything else in the scene. To illustrate this idea, we can use the system developed in our work and selectively image just the surface of a teapot, resulting in images where the light from every other part of the scene is optically blocked. These light curtains are robust to scattering and offer a level of privacy completely optically, making them a powerful tool in the real world. For example, such devices are being explored in the context of autonomous driving for collision avoidance, to identify when objects get too close for comfort. Such a setup can be created by using a rolling shutter camera combined with some sort of light projection system. In short, every row of a rolling shutter camera captures a different slice of the scene at a different time. If we synchronize a projector with this camera, we can illuminate a different pattern for each individual row of the rolling shutter. It is this spatio-temporally varying illumination that forms the light curtain. Objects that intersect this light curtain will be visible to the rolling shutter camera, while objects that don't will be too dark to be seen. Such a system requires that the projector is fast, programmable, and light efficient. However, existing techniques don't really satisfy all of these requirements, so we turn to a holographic approach. In particular, if we combine a binary digital micromirror device with the Fourier transforming properties of a lens under laser light, we can build a projector that is fast, programmable, and light efficient. With this system, we can create complex light curtains that were impossible for previous approaches. This may enable new applications for light curtains, such as in human-facing robot safety, creating touch interfaces from arbitrary objects, and measuring scene disturbances. Thanks for listening, and please come to our poster for more details.
We present a method for leveraging common structure for prior free image reconstruction. In image reconstruction problems, the goal is to recover a ground truth clean image, which we call X, from a noisy corrupted version called Y, where X is degraded via some known forward model F. This problem is highly ill-posed, so it is often solved using priors or regularizers through regularized maximum likelihood. However, these priors can exhibit human bias or require many clean data examples. We define the additional constraint to be the image generation model M, or IGM for short, which captures our assumptions or knowledge about the underlying image. In this work, we consider solving inverse problems without an image generation model or access to ground truth images. The key insight of our work is that knowledge of common structure across independent problems is sufficient regularization alone. First, we show that a variant of the evidence lower bound, or elbow, can help perform IGM selection. Suppose we have a noisy image of a 3, and we have access to IGMs to generate images of 0s, 1s, 2s, and 3s. We would like to select a model from these choices. We show in the paper that a variant of the elbow, called the elbow proxy, can be used as a criterion to select the correct model, in this case a model for 3s. Additionally, we consider learning the IGM from a collection of noisy corrupted measurements where the underlying images share a common structure. We demonstrate that one can capitalize on this common structure and optimize the elbow proxy to learn an IGM. The key assumption here is that ground truth images share a common structure, but we cannot image them directly. This is true in many scientific imaging problems like black hole imaging and medical imaging. We demonstrate learning the IGM from denoising 75 images of a face. Our reconstructions remove much of the noise and have high fidelity to the truth. We are also able to reconstruct a video of an evolving black hole. Please see our project page for more details.
Hi, my name is Felipe, and today I will be talking about compressive single-photon 3D cameras. A single-photon 3D camera estimates scene depth by measuring the round-trip time of a light pulse. This is done by building a histogram of the time of arrival of each detected photon, whose peak gives a reliable estimate of scene depths. With this conventional method of building photon histograms, the data bandwidth required scales roughly linearly with the desired depth resolution. Consider a 1 megapixel scene. A full resolution histogram will require data rates over 100 gigabytes per second. This exceeds the speeds provided by the fastest data buses available today. Using a coarse depth resolution, we can bring this down to reasonable USB 3 data rates, but the depth map accuracy will suffer. This raises the question, can we capture a compressed version of these histograms while still maintaining high depth resolution? In this paper, we present a linear compression framework based on the coded projection of timestamp data with a coding matrix, which can be applied in an online fashion as each photon is detected. We evaluated different coding matrices on real-world experimental data. Using a coarse histogramming approach with 8 time bins results in a low-quality reconstruction. Using a truncated Fourier matrix can greatly improve the results. We propose a coding matrix based on gray codes, which achieves even higher quality reconstructions. Now consider a flash LiDAR scenario. If we use a truncated Fourier matrix, we obtain the following depth image. Although the depth image looks reasonable, if we look at the depth errors, we find that there are significant errors due to indirect light reflections. If we design the coding matrix to include high frequencies, then these errors can be greatly reduced as shown in this slide. To summarize, we have proposed compressive histograms as a practical approach to compress high-resolution single-photon 3D data in an online fashion. Thank you.